Good afternoon. This lesson is going to be covering titrations. We'll first learn about the math for working through the titrations, and then we will distinguish key differences between strong acid, weak base, strong base, weak acid type of titrations, and also incomplete titrations, learning how to calculate the pH at any point along the titration process. And finally, we will look at the polyprotic acid titrations as well. So we're going to start off with a quick review for our titration curves. A titration, again, is a method that we use to determine the amount of an acid or a base in solution that is of unknown concentration. I just want to stress at the very beginning, this is nothing more than a limiting reactant problem in its easiest form. So you will have some situations where we have to do a little bit more complex math that's involved with it. You will have problems where you have to have a weak acid or a weak base equilibria set up. You'll have other problems where you're going to have the salt hydrolysis, and you're going to have the Ka or Kb of the salt to determine the pH as well. But in its simplest form, it starts with just being a limiting reactant problem. So don't let that intimidate you along the way. When we are looking at these, we have the substance of known concentration. If you remember, we call that the titrant from our video on the lab portion for the titration curves. It is going to be delivered from a device that we call a burette, which is basically like a graduated test tube almost, with a little opening at the end. And then we're placing that solution into a unknown solution dropwise until we have completely reacted the entire analyte. The analyte is the unknown solution that we are trying to measure. A couple of key points during your titration curve. The first one is your equivalence point. It's also called the stoichiometric point. And that is the point in the titration when enough titrant has been added to react exactly with the amount of the analyte that is found within the beaker. The key thing that we can remember with the equivalence point, again, it's not always going to, because you're neutralizing the substance, again, that perfect neutralization between the acid and the base, it's not always going to have a pH of 7. That's where we get into the different types: strong acid, weak base, weak acid, strong base, strong acid, strong base. Those things can change where the equivalence point is located on the pH scale, and that's due to the fact that when we hit the equivalence point, we have completely neutralized the acid and the base, so we know that the moles of the acid will equal the moles of the base, and almost more importantly, in many cases, it will also equal the moles of the salt. So when we're looking at those types of reactions, a lot of times to determine the pH for the solution, we have to look at the salt hydrolysis, and being able to get the concentration of the initial salt is very important. The endpoint, that is signaling the end of the reaction by looking at a color change for an indicator. We'll talk more about the indicators as we go, but essentially what we always like to do is we want to choose an indicator that will have the endpoint occurring just after the equivalence point. So we want the endpoint to occur just after. I'm just going to do equivalence point as EQ here for us. So it's just after the equivalence point. That way we know we have completely reacted all of the analyte. And if we do it beforehand, depending on the type of the reaction, you could have, if you do it before, just having a pH unit of 2 difference for your indicator choice could be upwards of 4 to 5 milliliters of the titrant that you're not adding to neutralize. So it could make a very big difference in the amount of the analyte's concentration that you're missing. The last thing, again, when we were talking about our pH curves, our titration curves, you are creating a graph where you have the volume of the titrant on the bottom. So put that volume of the titrant, could be acid or a base, and then you have pH as your y-axis. So you're plotting pH versus the volume of the titrant. So now you can see the physical setup that we would use for a titration experiment. In this technique, as I said, you have this burette, which you have the known solution. Again, that could be a primary standard, it could be a secondary standard. We talked about that in the lab as well, trying to verify what the concentration is of the known by reacting it with a certain mass of, if it's a base, the KHP. If it is an acid, we would use sodium carbonate for that instead, so that way we could verify the concentration of the known substance. And then from there, we could test that against the analyte, which would be down here in the beaker. So this again, I'd have my analyte down here in the beaker, the unknown concentration. We can set it up with a pH meter so that we could then measure the change in the pH of the solution as we continue to neutralize the analyte with your titrant. Again, we can use pH meters. You could do it the old-fashioned way where you would have to sit there and take test strip readings of it as you go, but it is much easier to just have our computer programs to come in and constantly show us a nice graph of the pH changes that would occur over time. So at the equivalence point, that's typically where we'd want to try to stop the reaction, but that equivalence point is again where the moles of the acid equals the moles of base and equals the moles of salt. So I wanted to take a moment to focus on how to choose your indicators properly. So first off, you have indicators just simply being another weak acid system that undergoes equilibria reactions that have different colors for their weak acid versus their conjugate base. So I'm just going to kind of draw this out, and you'll see it labeled as HIN for your indicator. So I can have the indicator going into water producing H3O plus and then the IN minus. So again, the weak acid would have some particular color associated with it. The IN minus would have a different color that is associated with it. Each one of these has a value of Ka for that particular reaction. Now, when we choose our indicators, we typically can look at taking something like this, where we haven't talked about this before, but anytime that you have that negative log, that just basically stands for the P as in pH. So if I took the negative log of the Ka, we would just simply call that the pKa. Works the same way as it does for pH. We're trying to make a number for scientific notation that's either really, really small or really, really large, a more usable number. So when we look at this type of thing, to choose our indicator, we can take the pKa and we can add or subtract 1 from it. So that gives us basically a 1 to 10 ratio in either direction of the IN minus to HIN concentration. And so choosing your value for the pH for projecting the equivalence point, you can relate that to the pKa for the reaction. So if I know I have a strong base and a weak acid that are reacting together, I know that I'm going to have a pH that's above 7. So I'd want to choose a pKa value that would also be above 7, maybe something like 9, that would allow me to have the pH change between 8 and 10, because that pKa plus or minus 1, that's going to allow me to see the basic pH range of when the color changes will occur. The indicator can be used to find the equivalence point in a titration as long as it's changing color in the small volume change region where that pH rapidly changes. So you're going to see a huge spike in the titration curve, as we've already discussed in the previous titration videos. And so what you can then see is just finding that small little range where we expect the pH to change, choosing an indicator that is proper for that. So you can now see the big difference in your indicator choice and how that can affect your rationale for the unknown molarity for your particular analyte. You have many different types of indicators that we can use. Phenolphthalein is a very common one that gets used for a strong base, weak acid type of titration. And you can kind of see here as we look at the phenolphthalein in the upper left-hand corner, excuse me, it has a color sensitive range between 8.3 and 10.0 for the pH. So if I'm doing that for that strong base, weak acid, then I have a very good chance that my color change, as you can see going between here, that's in the steepest part of my titration curve. And so as a result, it's not going to have a large variance in the volume of the titrant that I'm adding if it is, say, a Ka for the, or the equivalence point for the reaction is at 8. It might show up at 8.3, but as you can tell from the graph, that steepest part, it's going to basically change its pH by 3 to 4 units at least, just by adding 1 milliliter of the titrant. So it's really not that big a deal. However, if we did the same reaction, but we chose methyl red as an indicator instead of the phenolphthalein, you can see that the range for the color change of the methyl red is between 4.2 and 6.0. So whereas we reach the equivalence point here at the 50 milliliters, you can see that the first time that I would see the color change occurring would be right over here. And that would be somewhere approximately at 15. So I would see the color change occur and go all the way from 15 up to about 45. And at that point, I would think, oh, I'm already done with the titration. And I would have a much more concentrated analyte projection than what is happening in reality. Because again, I would think that it would be starting to reach the equivalence point somewhere just after 15 instead of at 50. So you can see in this diagram the importance of properly choosing your indicator, because again, it can make a big difference on where you think the equivalence point is compared to where it actually is in reality. You can also see here, we're now looking at a different example on the last one. This one is going to be where the acid is now your titrant instead of the base. So you can see the analyte pH starts off extremely high off the screen at like 13, and then it drops way down and comes down to about 1. A little over 1. So you can tell with this one it's going to be a strong acid, strong base titration. Notice the large gap here. We're talking about the pH range here for 1 milliliter being added. You have about 8 pH units that occur. So in something like this, if you use the phenolphthalein indicator, it wouldn't make that big of a difference. It would be slight, but it wouldn't make that big of a difference compared to the methyl red. But especially when you are doing your weak acid or weak base concentrations involved in those titrations, you can see a very large difference in the values for the concentrations being added. So I quickly wanted to give you a little diagram here that gave you a list of all the different ranges for some of your different indicators. So you can see here we basically have something for every single pH range along the way. And so when you have a mixture of all of these different equilibrium systems together, that's where you get your universal indicator that you may have used in some of your lab experiments. So when we're looking at this, I'm going to post this onto OneNote for you, this little diagram here, so that way you always have that available to you when you are initially working through your problems. But trying to decipher which one would be the best, all you have to do is compare the pKa to what the projected equivalence point should be for the reaction, and then just try to get it 1 plus or minus the pKa for the desired equivalence point. Okay, so I'm going to start to work through all the different types of titrations that we can do. And I'm going to try to give you guys some diagrams here so you can kind of see what's taking place within the solution as we go. This is that really important part where we've tried to do it a couple other times, identifying what are your major species in solution, what are the minor species in the solution as you go through this process, and then figuring out what is going to be the part that actually affects the pH of the solution. So we're going to begin with a titration between a strong acid and a strong base. From the very start of the titration to near the equivalence point, the pH is going to go up very slowly. Now, from a conceptual standpoint, I hope that'll make sense, because if I'm starting with either a strong acid or a strong base, remember, any of these have 100% dissociation that's taken place. So you'll see here, especially at the very beginning, that very level increase in the pH as you go through a lot of the titrant being added. Reason being, again, I have a large surplus in solution. Every single H plus or Cl minus in this case, or the A minus for any of your strong acids, 100% dissociated. So I have a large amount of H plus. So it's there as it has the OH minus added in from the NaOH in this case. They can immediately neutralize that OH minus that is coming into the solution. And so as a result, there's not a large change in the H plus concentration. And so it makes it a very slow rise as it goes. Just before we hit the equivalence point, again, now you can see this is where we start to get a very rapid increase in the pH. That's because nearing the equivalence point, we have very little of the H plus or the OH minus, depending on the situation, that is still left in the solution. So by adding a little bit of the titrant, you're going to now flip the scenario. Instead of the analyte being the excess reactant in our limiting reactant problem, now whatever's in the burette is going to become the excess reactant, and so I have the excess of either the H plus or the OH minus coming in dropwise, and that's what's going to have that rapid change in pH. And then eventually, as we continue to increase the concentrations, you're going to see a leveling off of the pH again towards the end of the titration. So I wanted to go down and focus again on the particulate diagrams down here on the bottom. AP exam are always getting more and more in this direction of having you guys analyze the diagrams. So if you think about before the titration begins, all I have is HCl in the beaker for my analyte. 100% dissociation. So I have H plus, I have Cl minus ions all throughout that mixture. As we begin to add in the base, the NaOH from the experiment, now I have Na plus ions that would be present. I have the Cl minus ions that would still be present, so I'm starting to form the sodium chloride, but notice I don't have any OH minus ions, and that's because of the fact that all of the H plus that was already in the solution immediately consumes the OH minus to produce water molecules in the solution. And so all I have left are the excess H plus, but notice the amount of H plus, as we notice here, I had 2 to begin with. Now I'm down to only 1. So I'm losing some of the H plus from the concentration of the solution. And then once we get to the equivalence point here, where the number 3 is, that would be right here on our graph. Now I have the H plus completely neutralized by the OH minus. So notice all I have in solution, Na plus, Cl minus from the reaction vessel. And so I have no more of the H plus or OH minus. So that's where we'd have our pH equaling 7. And then finally, once we get above this point, that would be anywhere in here would be the number 4. Anywhere in that vicinity, what we're looking at here now is I have the Na plus, I have the Cl minus, but now I have the additional OH minus because there's no longer any H plus present to neutralize it. And so I flipped the script over here. The H plus was the excess reactant to begin with, and now I have the OH minus that is in excess after the equivalence point. So I'd have my buildup of the OH minus, so now I have my pH above 7. Let's now look at a titration between a strong base with a strong acid. So we're basically going to flip the script, and now instead of having the strong base being my titrant, we're going to have the strong base being my analyte. And you can tell whatever one's the analyte by looking at the initial pH of the solution before any of the titrant has been added. So if you notice, my analyte pH initially is somewhere between 12 and 14, so in this case probably a little less than 13 based on the picture. So I know because my initial concentration is greater than 7 that it's going to be a base, and so that means that the strong acid in this case will be in my burette, and that would be my titrant. So we're going to have the pH starting off with a very, for the basic solution, very high. Typically your strong bases would start off above 12, and your strong acids would start out below 2. So that's kind of one of the ways that you can tell for your titration curves, is that you have a strong acid, strong base titration, is that starting point and ending point for the pHs, and then also that very flat region, especially right there at the very beginning. You have that very flat region where the pH is a nice gentle slope going up or down depending on the situation. So pH equivalence point, always 7 for strong acid, strong base, whether you have the base as the analyte or as the titrant. So let's now look at an example problem. So determine the volume of the titrant and the pH at the equivalence point when 0.1 molar HNO3 is used to titrate a volume of a solution containing 0.3 grams of KOH. So as we begin with, first thing I want you guys to do, identify your titrant and your analyte and determine whether they are a strong or weak acid or base. So the first thing, since I have HNO3, I know that would be a strong acid. KOH, that would be a strong base. So in this type of situation, we know and can answer the first question very simply. pH for this particular solution once neutralized will be equal to 7. Strong acid, strong base, neutral salt, in this case KNO3 would be forming, and as a result will not hydrolyze water. So now the second part, we have a titration formula. If you don't remember, we have the number of H plus ions per acid molecule. Remember, I abbreviate acids as MCs. Number of hydrogens per acid molecule times the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base multiplied by the number of OH minus ions per formula unit for the base. So when we look at this type of scenario here, we need to figure out how many moles of the KOH we have. So if you remember the product of MB and VB, that would be my moles of B. And if you remember at the equivalence point, moles of the acid equals the moles of the base. So I'd have this here as my moles of the acid. So when we're trying to work through this problem, we need to just determine the moles of the base. We don't have a volume of the solution for the base, but it doesn't matter because, again, I have the 0.3 grams, so I know I can figure out how many moles are present for the base. So I'm going to start off to calculate my moles of the KOH. I'm going to take these 0.30 grams, and I'm going to divide that by its molar mass. So 1 mole of KOH would be the equivalent of 56.11 grams using your molar mass on the periodic table, and that would give you 0.0533 for your moles of KOH. So since that's my moles of KOH, using my solution, which is 1.1 molar, I know that would also equal the equivalent number of moles of the nitric acid. So at this point, since I have the moles of the nitric acid, and I know that I have 0.10 molar HNO3, that would be equal to 0.00533 moles of HNO3 divided by the volume. So I could rearrange my equation to solve for V, just multiply B on both sides, divide by 0.1, and that would give me 0.0533 liters of the HNO3. But again, not really as easy number to work with, so we could take that, multiply it by the 1,000 milliliters per liter, and that would give us a final answer of 53.3 milliliters of the HNO3 that must be added to neutralize 0.3 grams of KOH. So now let's look at how we calculate the pH during a titration. And we're still going in the same type of avenue, looking at a strong acid, strong base component. So notice here I have my NaOH, strong base. I have my HCl, strong acid. So when you guys are doing any of your calculations during the titration, I highly recommend using a rice table. So you know how I am. I love you guys to use rice tables for any limiting reactant problem, and it will be the most effective instrument that you can use to solve these problems. So I have my balance equation. I have the NaOH, the HCl, NaCl, and H2O. So there's my neutralization reaction. That's the main reaction taking place in the solution. You'll have to differentiate between the weak acid equilibria or weak base equilibria versus the neutralization reactions as we progress through this lesson. So it asks us to calculate the pH when we have 49 milliliters and 51 milliliters of a 0.1 molar NaOH solution has been added to 50 milliliters of a 0.1 molar HCl solution. So two things that I want you guys to notice. Number one, I have equal molar concentrations. 0.1 molar NaOH, 0.1 molar HCl. So since I have a volume of 50 milliliters of the HCl, then that means that I'd have to have the same quantity, 50 milliliters, in order to neutralize the HCl with the NaOH. So now as we get into our problem, like I said, we have a limiting reactant problem. So let's set up our rice table that we would have. So when I have the NaOH initially, 49 milliliters. So if I do the 49 milliliters times the 0.1 molar, I'm going to leave it as the milliliters here instead of converting it to liters. It's just a little bit easier to use. So try to get comfortable using millimoles in the process. It will be very helpful for you. So if I have 49 milliliters times the 0.10 molar, that will give me 4.9 millimoles. And then for the hydrochloric acid, we know that we have 50 milliliters times the 0.1 molar for that concentration, and that's going to give us 5.0 millimoles. So obviously here 1 to 1 to 1 to 1 ratio, so minus x plus x for those values. As I go, I would have 4.9 millimoles equaling x versus 5.0 millimoles equaling x. So in this instance here, I know that the NaOH, what was in my burette, is still my limiting reactant. So if I take this value here and plug it in to solve for my overall amount of moles that are left over, I'd have 5.0, and I'm just going to do this underneath here, 5.0 minus the 4.9, that would leave me with 0.1 millimoles. Now the reason why that's nice, because I have to divide by the total volume of the solution, instead of having to convert both of those back into the molarity by doing it into liters, now all I have to simply do is take the 0.1 and I can divide it by the total volume, which is just 99, and that gives me 1.01 times 10 to the negative third molar HCl. Remember, volumes are additive, so since I have 49 plus the 50, my new total volume for the solution, I'll do that here real quick. So my total volume would now equal 49 plus 50 for a total of 99 milliliters. So I divide that out, I get 1.01 times 10 to the minus third molar HCl. So you can see we're really super close to having the equivalence point being reached. Only need one more milliliter, but if I take the negative log of that answer, again, I'm going to have something. If I take the negative log of the 1.01 times 10 to the negative third, that's now going to give me a pH of approximately 3.00, 2.996, but we can round that up. So I have a pH equal to 3. So 1 milliliter away, I'm at a pH of 3. Now, let's do the same thing, but this time, let's flip that script, and I'm just going to put my I, C, and E down here. But for part B versus the part A, we now have 51 milliliters of the NaOH. So same type of scenario, I have the 51 milliliters times 0.10. So I have, in this case, 5.1 for my millimoles of OH minus. I still have the 50.0 milliliters times the 0.10 molar, and so that is going to give me 5.0. Rewrite that a little better. Still have 5.0 millimoles of the HCl. So minus x minus x. Now hopefully you can tell my x here would be 5.1 millimoles. Again, just setting it equal to 0 since it's a limiting reactant problem. 5.1 millimoles versus the 5.0 millimoles that we had for the hydrochloric acid. So in this case now, the 5.0 is my limiting reactant. So the OH minus is now the excess. So notice again, the script has flipped after the equivalence point because of the fact that I now have the titrant being an excess instead of the analyte. So now when I come over here and I just set up my equation, 5.1 minus the 5.0, that now gives me yet again 0.1 millimoles, and I'm going to just take this and come over here. So to find my total volume of the solution, I add them together. So for part B, I have the initial 50 plus the 51, so I now have a total of 101. So if I take 0.1 and I divide it by 101, now I'm at 9.9 times 10 to the negative fourth for my molarity. And if I take the negative log of that answer, that gives me now negative log of the 9.9 times 10 to the minus fourth, not 14th. That now gives me 3.004. So again, approximately 3.00. But instead of that being the pH, that is now my pOH. So 14 minus the 3.00 would give me a pH in the solution equal to 11. So notice, just by adding 2 milliliters of the titrant, I went from a pH of approximately 3 to now being 11. So that's why I was saying in that small region where we're talking about adding the indicators, if it's a strong acid, strong base, you can see that just that little bit of extra titrant being added causes a huge jump. So you're not going to notice as big of a difference in the molarity of the unknown by using the indicator improperly for the strong acid, strong base, but you would notice it greatly for a weak acid or a weak base being titrated with a strong component. So again, I just wanted to show you, illustrate that fact here with the particulate diagram. As I had mentioned, note that the pH is increased by only 2 units, from 1 to 3 when we started off the reaction by adding the first 49 milliliters of the base. Only a difference of 2 pH units. But the solution, when adding 1 extra milliliter or 2 extra milliliters of the base when we approached the equivalence point, jumped by 8 pH units. And that's just due to the amount of the H plus that was left in the solution as the equivalence point was approached and then surpassed, and you had the excess OH minus that was present. So you can see here in the diagram, again, same type of concept. As we are approaching that equilibrium, you have the H plus and the Cl minus initially. You have the Na plus being added in, OH minus being neutralized. We have exactly 7 for the pH at the equivalence point, no H plus in solution. So again, we're getting really, really minute amounts. And then as we go on, you have the extra OH minus that's been added into the solution, causing the pH to rise above 7. So again, just wanted to illustrate that, especially getting into the focus of the first 49 milliliters of the base being added. You had only an increase of 2 pH units versus the final 2 that we added, causing it to jump 8 pH units. Okay, so we're now going to get to the fun stuff. Titrating the weak acids with a strong base or a weak base with a strong acid. So the first part, when we want to determine the initial pH of the solution, we're going to use the Ka to determine that, just like we did at the beginning of the unit, where we have the initial concentration of the acid or the base. We're going to use the Ka or the Kb to plug that into our expression, solve for X, and determine the pH of the solution from that. Structurally speaking, this is the huge part difference-wise. You got to remember, when we're talking about the weak acid or the weak base, they only partially dissociate. So if we are looking at the diagram down below, we can see some key differences between the strong acid, strong base. If you remember, when we were dealing with the hydrochloric acid, we had 100% dissociation. So I saw H plus, I saw the Cl minus ions that are in solution. You'll notice, however, that for our first part, which would be at this point on the diagram, all I have essentially for the vast majority of that solution is just the parent acid molecules. And so there is not much H plus solution in the solution. And so key difference, what you can see to let you know that you have a weak acid versus a strong acid, even if they're equal concentrations. The strong acids typically will have a starting pH below 2. The weak acids will have a pH between 2 and 4. Now, the other key structural piece of your titration curve that allows you to notice a weak acid is being used instead of a strong acid. And this relates again to what is taking place in the solution initially with the acid reacting with the water. So notice I have a beginning hook to my titration curve. That initial jump in pH, whereas we had that nice solid gentle slope going up for the titration curve for the strong acid with the strong base, now I have an initial jump. And the reason being goes back to that partial dissociation. because I have only a little bit of H plus ions in the solution, when I first add in the OH minus coming from the burette, I now have that as an excess in the solution. So the little bit of the H plus that's already present is not enough to completely neutralize it. So I had that initial jump in the pH, but then the Le Chatelier's principle kicks in. So if I look at this particular reaction here, I'm just going to abbreviate the acetic acid as HAC. So I have HAC plus the H2O forming the H3O plus and the AC minus. So again, I have just a little bit of that H3O initially, but as I add the extra OH minus in, and this is why it's the same process, limiting reactant, whether it's strong or weak for that component, because I add the extra OH minus in, that's going to react with the H3O plus and form water. So again, think Le Chatelier's principle, whether you're doing it qualitatively with just looking at what's being removed from the reaction, I'm lowering the amount of product, so it's going to shift to replace the product, or you do it quantitatively, where we're now looking at my Q value for the product is lower than my K value because I lost H3O plus. The reaction must shift to replace it, so it's going to shift to the right. Either way you want to look at it, does the same thing. But as I continue to add extra OH minus, more of the HAC is going to dissociate to react with the OH minus. That's why you can see the slope kind of leveling off during that middle portion. The one thing that we're going to talk about later on in our next unit is getting into the buffer concept here. And once the reaction starts, you have created a buffer. So a buffer, by definition, is a solution of the weak acid and a salt of its conjugate base. So that way we have the ability to fight off a change in pH in either direction by adding another acid or a base. We'll talk again more about that. But this middle region here, that's going to be your buffered region for your titration. So I've got my buffered region in there. We'll talk more about the ideal buffer, about where we can look at pH and relationship to pKa's, all that kind of good stuff in the next video. But for right now, just understand that will give you a buffered region. And then the other big thing I want you to notice, the equivalence point. We did salt hydrolysis. Because I'm reacting a strong base with a weak acid, we expect that the equivalence point for the titration is going to be above 7 because I have a basic salt that is being produced. So notice my equivalence point is here, somewhere above 8, a little less than 9, so maybe 8.5, 8.7, something along those lines. So I have a pH above 7. So here's where, again, want to get into just the little small dynamics. Notice that my steep change in pH, the units are much smaller. So it might be a change in pH of 4 units for adding 1 milliliter instead of 8 like we had for the strong acid, strong base. So the steepest part of the curve, notice, is much smaller. Still finding the equivalence point by taking the midpoint between the steepest part of the curve, but you can see here that that change is much smaller. So if I use the wrong indicator, again, say I used one that was 5.5 instead of 8.5. Well, now I'm talking about having the equivalence point being reached somewhere over here around 35 to 40 milliliters instead of 50. So it can make a big difference in the overall molarity of the unknown. We'll talk about the Henderson-Hasselbalch for any stoichiometry involving the buffered region. Again, we don't really use the Henderson-Hasselbalch equation in its purest form anymore in AP chemistry, but I always like to show it to you guys to get you ready for college because it is important to be able to use it. Now, let's go back to our particulate diagram for just one more moment. So as I'm looking at this here, as the reaction progresses, start off again, no H plus or very little H plus in the solution, just the parent acid molecules. Notice as I begin to add, the extra OH minus is going to force the HAC molecules to split apart. So I now have the acetate ions The OH minus and the H plus neutralize each other to form water, and I'm left with the extra Na plus. At the equivalence point, when we get there, I have the acid being completely neutralized. I have Na plus in the solution. I have the acetate ion CH3COO minus in the solution. And then finally, after there's no acid left, still talking about at our equivalence point. So that's one little change here. So this is kind of 3, 4 in terms of our particulate diagram. We don't have any acid left to neutralize the OH minus. So as we go through this part here, again, at that equivalence point, you're going to have some of the water being hydrolyzed to form the acetic acid molecule, and then the OH minus, and then anything above here, that would definitely be in the 4 range, because now as we add the excess OH minus, there's once again no more H plus present to neutralize it, but again, the equivalence point is going to still have some OH minus present in the solution. Now, the other big thing I just want you to notice, because I'm dealing with a strong base in both situations, the last part stays the same. I still have my resulting solution still having a pH over 12. And that's just due to the excess reactant being the same. When we finish up, we still have NaOH in the excess left in solution, and so it's going to finish at the same point. So just to summarize here, again, looking at the ways that the weak acid titrations will differ from a strong acid titration, the initial pH is going to be higher for your weak acid than it will be for your strong acid. The stronger the acid is, and again, we mean stronger acid in terms of dissociating Ka values, the stronger the acid is, the lower the initial pH will be, but also very important concept behind that as well. You'll have a less defined hook at the beginning. And I'm just going to put that in abbreviations, because if you notice here, when we start looking at the red line, Ka of 10 to the minus 2, notice that hasn't really changed much with that little initial burst, because hopefully you can make sense. The larger my value for Ka is, the greater amount of H3O plus I have in the solution. A greater amount of H3O plus that's there already can react with the OH minus that is being added to it. So as the Ka for the acid gets smaller and smaller, weaker and weaker the acid, notice the pronounced look of the hook at the very beginning, to where with this last one with the Ka of 10 to the minus 8th, you have a pH jump almost like it's at the equivalence point of probably about 2 pH units just by adding in a couple of milliliters of the strong base to it. And then notice also the size of the change in the pH as we approach the equivalence point. As we get weaker and weaker for the acid, the slope now changes. It is less pronounced for that difference. Where we get to the point with the Ka 10 to the minus 8th, you're talking about having a pH range change of essentially 1 or 2 when we get to being within a milliliter or so of the equivalence point. So there's not much of a change, whereas for the stronger weak acids or the stronger strong acids, again, we're talking somewhere between 6 and 8. Notice here the ending point, because we're using the same strong base, the ending point looks exactly the same for all of the different titrations. So big points of difference: your initial concentrations leading to a change in the initial pHs as you get higher up. With the Kas, again, higher pH, that expresses weaker acid. The more pronounced hook on there, that also tells you weaker acid. And then finally, the last part, you can see the equivalence point goes up much higher above 7 as we get the weaker the acid for that particular titration. All right, so let's now look at an example between a weak acid strong base titration. We're going to calculate the pH in a solution formed by adding 10 milliliters of 0.05 molar NaOH to 40 milliliters of 0.025 molar benzoic acid, and they give you the benzoic acid being a Ka of 6.3 times 10 to the minus fifth. So the first thing that we're going to do in this situation is see what we have left over in the solution. Is it the excess NaOH or is it excess benzoic acid? That's going to determine what we have to do to solve for the pH of the solution. So I'm going to start off here and I'm just going to abbreviate the benzoic acid as being HBZ for us. So I'd have HBZ plus the NaOH forming, again, NaBZ and H2O. So again, this is just my abbreviation here just to make it a little bit easier to write out. So I'm starting off my rice table to determine what I need to do. So in this particular instance, I have 40 milliliters of the 0.025. So that's going to give me a total of 1 millimole. And then for the NaOH, we have 10 milliliters and 0.050 molar, and so that will give me 0.50 millimoles of the NaOH. I have still a 1-to-1 ratio, so determining limiting reactants, everything adding up to equal 0, I'd have 1.0 minus x equals 0, so my x in this case would be 1.0 millimoles. And 0.50 minus x, 0.50 minus x equaling 0. I know that my x over here would be 0.50 millimoles. So as far as my limiting reactant is concerned, I know that the NaOH would still be my limiting reactant. So here's where things come into play. So my excess, now I know, is still my weak acid. So that means that the weak acid concentration that I would have left in the solution, if I would set this up and say 1.0 millimoles minus the 0.50 millimoles equaling 0.50 millimoles left over, I now have to take into account my total volume of the solution. So I have 10 milliliters plus 40, so 10 plus the 40 would give me a total of 50 milliliters of the solution. So I'm going to divide that by the 50 milliliters. Again, the millis cancel, leave me with moles per liter, and that would give me 0.010 molar for the HBZ concentration. So now, as we go through this little process here, that means we have to go back and look at what is taking place in the solution. But in this case, we also have to focus on this. What was the amount of salt that was created? So by adding plus x, I'd also have 0.50 millimoles divided by the 50 milliliters. So I also have 0.01 molar NaBZ as well. So that's going to change some of the dynamics of this type of problem. So when I look at this reaction, we're now going to get into our buffer type of concept here, but I have my equilibrium reaction for the HBZ. Since this is still found in excess from our reaction, I know that it is still going to react with the water to then produce more of the H3O plus and the Bz minus ions. So when I set up my rice table, I initially would have the 0.010 molar, and I'd have the 0.010, oh, sorry, not that one. That would be a 0 here because it's been all neutralized. And I'd have 0.010 molar Bz minus at the point where we've added the 10 milliliters of the base. So in this case, because I still have the 0, this would be minus x, this would be the plus x. So setting up my expression, I'd have 0.010 minus x, I'd have 0, and 0.010 plus x. And so at this point, the value for x is going to be really small, so I can set up my expression, the Ka, 6.3 times 10 to the minus fifth, that's equal to the H3O plus times the Bz minus over the HBz concentration. So at this point, I can plug in, here's my value for x, this would be 0.010 plus x, 0.010 minus x, but again, we can make the assumption that x is going to be really close to 0. Because this is 0.01, this is 0.01, we know that these two amounts can cancel off, and at that point, my x value is equal to my Ka. So if I know that H3O plus is equal to 6.3 times 10 to the minus fifth, and I took the negative log of that value to equal the pH. Now, if I plug that in, the negative log, 6.3 times 10 to the negative fifth power, we get a pH equal to approximately 4.20. Okay, so we just got done figuring out the pH of a solution at some point during the titration process. Now we're going to focus on calculating the pH at the equivalence point. So at this point, remember, due to the fact that we're at the equivalence point, we know that moles of the acid equals moles of the base, and in this case, the most important part, moles of the salt. So I have the pH that I'm trying to calculate for a solution formed by adding 0.1 molar HCl to 20 milliliters of 0.1 molar NH3. So I just want to start off the problem here, making sure you understand. Use a little bit of logic. What should my pH be at the equivalence point? Well, notice I have a strong acid and I'm reacting that with a weak base. So I'm going to have an acidic salt. So therefore my pH at the equivalence point should be less than 7. So I have my reaction here of NH3 plus the HCl forming, in this case, NH4Cl and the H2O. Now, the other reaction that we would have in this process is going to be dealing with the NH3. So initially, in that solution, I would have the NH3 reacting with the water, forming my salt, NH4 plus, and the OH minus. So as we go through this process, remember you'd have a Kb that would be associated with it. If you looked at Kb up, it's 1.8 times 10 to the negative fifth for that value. Since we're talking about at the equivalence point, I know that I've added the perfect amount of the NH3 and the HCl together. Now, the one thing that we have to do for this problem is we need to determine how much of the HCl would have been added, would have been added to the 20 milliliters of the NH3 to completely neutralize it. So same type of concept, I can use the my pen will work. My MA times VA equals MB times VB formula. I know that for the acid, it is equal molar, so I'm not going to have to do this all out in this particular instance, but because I have 0.1 and 0.1, I know that the volume is the same because I have one ionizable hydrogen here, and the NH3 is only going to add one hydrogen to it, so they're both monoprotic, so therefore the volume would be the same. So again, if you can just envision 0.1 times x equals 0.1 times 20, I get that same answer. But if it weren't equal molar amounts, you would need to use this formula to determine what that value is. So just so you can kind of see that illustrated, 0.1 times the VA equals 0.1 times 20 for my milliliters. Again, my VA, because this and this are identical, my VA would also be 20 milliliters. Now, big grand scheme of things, that's not really important as far as calculating anything out other than what my total volume happens to be. So because I have 20 milliliters here and I have the 20 milliliters here, that now tells me that my total volume for the solution would be 20 plus 20, or 40 milliliters. So now the other aspect of this, we need to determine how many moles of the salt would be forming. So if I'm starting off with 0.10 molar times 20 milliliters, that would equal 2.0 millimoles. And it's not wanting to cooperate here. So I'd have 2.0 millimoles. Rewrite that here. Sorry, my pen is not wanting to cooperate. So for my I would have that. My C minus X. Here I'd have 0. We know I've got the same amount over here for the HCl. So therefore, I know I'd have 2.0 millimoles of the NH4 plus ion. But now to get the concentration, I'd have to divide it by the 40 milliliters. So if I do the 2 divided by 40, that should give me 0.05. So I have 0.050 molar for the initial concentration of the NH4Cl. Remember, NH4Cl, completely soluble in water, so it will split up into NH4 plus and Cl minus. Cl minus, coming from that strong acid, will not hydrolyze water, so I want to focus on the NH4 plus. So that now gives me a new reaction to focus on for what's taking place in solution. Again, the reaction, depending on the point in the titration, can have a completely different significance for us in our work. So you have to be able to kind of go back and forth and figure out which one you need to use. So I have the NH3 and the H2O going back to the parent base. So now if I'm starting off with 0.5050 for my molarity, I'd have minus X, and plus X, and that should be H3O plus, excuse me, for those. And the other thing that we need to do is calculate the Ka. So remember, I gave you the Kb, 1.8 times 10 to the minus fifth. So we can take the Kw, divide it by that Kb value, and we have 5.6 times 10 to the minus 10th for the Ka. So I have very small Ka, so the change in X, negligible. So I can then take 5.6 times 10 to the minus 10th equals now X squared over 0.050. And notice this one's going to be a little bit different than the previous one. I don't have any NH3 that's present in solution because it's been completely neutralized in this case. So it's going to change up the dynamics just a little bit because I'm dealing solely with what's there for the salt. And so now when I multiply that out, that gives me approximately 2.8 times 10 to the minus 11th equals X squared. So if I take the square root of that answer, I'm going to be somewhere around 5.3 times 10 to the minus 6. So if I now have that being set as my H3O plus concentration to solve for pH, I take the negative log of that value for X, and that ends up giving us a pH of approximately 5.28. So again, notice just slightly acidic. Again, 5.28, just slightly below 7. So my answer makes sense with what we would expect to occur. Okay, so for our last problem here, we're going to try to determine the pH for the solution after the equivalence point. So again, changing up what is my limiting reactant. So I'm going to do the same thing, set up my rice table. So I have the NH3 reacting with the HCl, forming the NH4Cl and the H2O. So same type of concept. Notice though, again, for this I have the 20 milliliters times the 0.10 molar. So that's going to give me 2.0 millimoles of the NH3. I have 30 milliliters times the 0.10 molar, and so I'm going to have 3.0 millimoles now for the HCl. The total volume for my solution, I have 20 plus 30, so I have a grand total of 50 milliliters. So now when I do my minus x and my minus x for my rice table, I now, in this particular instance, am going to have my x value here equaling 2.0. My x value here would be 3.0. So in this particular instance, I know that, again, the NH3 has been completely neutralized. It is my limiting reactant. So I can plug that in just like we did before. So I'd have the 3.0 minus 2.0. So that's going to give me 1.0 millimoles. I have my total volume of the solution being 50 milliliters. And so if I do 1 divided by 50, that gives us 0.02 for the molarity of the solution. So now at this point, that is my excess. Again, the amount of the salt in this case is not necessary because from our mixture of acids, remember, strong acid mixed with something that's weak, you just worry about the concentration of the H3O plus coming from the strong acid because that concentration would shift the equilibrium. So if I take this here as my excess HCl solution, that will also tell me that I'd have 0.020 molar H plus. So I can take the negative log to solve for pH. I can take the negative log of 0.02, and that will give us a pH of 1.70. Simple as that. So you can notice in this case, because the strong component is the excess, it makes it super easy. We just have to determine the concentration of that H plus or OH minus from the strong component, and then plug it in and solve. And that's it. All right, last slide. I know I've made this one kind of long here, so I'm going to try to be as brief as possible with this, but I wanted to just briefly introduce you to the titrations for your polyprotic acids. So when we talk about the polyprotic acids, remember they have multiple hydrogens that can be ionized, and so it goes through a stepwise process for that neutralization, just like it does for the ionization. So for your polyprotic acids, you're going to have multiple equivalence points. So when we look at it, you can remember that for a particular polyprotic acid, you could have a beginning point. So if I look at something simple, just as an example, like H2SO3, that first ionization, when I add it to water, I would have H3O plus, and I would have HSO3 minus. And then for the second ionization, I'd have the HSO3 minus reacting further with some H2O, forming more H3O plus, and I'd be left with the SO3 2 minus ion. So as we go through this process here, again, each one of these ionization steps would be the same thing when we are trying to neutralize them. The first part that we would see here, this pKa1 region, this would be associated with this top reaction here, and then I'd have the second as the pKa2 that would be up above. So at this point where I look at the equivalence point, that would be where I have completely neutralized the first of the H3O plus, and all I would be left with at this point in the solution would be just the HSO3 minus ion in that solution, plus the water and whatever the base cation would be. So in this case, the NaOH, so I'd have, or the Na plus. So as I begin to add more of the NaOH, now you'll notice, again, I start to have another rise in the pH, and that's due to the fact that, again, that pKa2, I'm now starting to neutralize some of the extra H3O plus that is forming from the HSO3 minus dissociating. And so I have that occur as well. I have my second equivalence point where now I have just the SO3 2 minus in the solution from the original acid, and then I have the Na plus as well. And then finally, once I get up above that point, as I add more, I would have just the excess, so this would be our excess OH minus ions that are in solution at this point, and so we could calculate the pH from that concentration. The one thing that I do want you guys to notice though is in terms of the volumes. Notice here, to completely neutralize the first step, it took 50 milliliters. To reach the equivalence point for the second step, it took 100. So the math doesn't change. I have equivalent amounts of the OH minus that have to be added to reach that next equivalence point, because again, stoichiometry matters. So I have the 50 milliliters as the volume that's required to get to each of the equivalence points along the way. So I just wanted to point that out to you guys. Like I said, I'll come back in our next video and we'll talk about using that Henderson-Hasselbalch equation so that you can see halfway to the equivalence point how the pH and the pKa are related to each other. So I apologize again, went a little bit longer than I wanted it to, but really important information, so I wanted to be very thorough with you guys. So again, please come to class tomorrow with questions, and I'll be happy to answer whatever I can at that point.